All right. Okay. So we're going to talk about vibrations. So the plan I have in mind for this set of lectures, so we have 2 hours today and 2 hours next week, will be to, first of all, introduce how we treat electrons and nuclei, because materials consist of both electrons and nuclei. So what we do, we basically will go through the adiabatic approximation. Then we will have a look at the treatment of vibrations in the classical physics first. And then, assuming nuclei are still classical, we'll try to discuss how to calculate vibrations using electrons as quantum particles, but nuclei is still classical. Then we will go to the quantum description of vibrations and what are the consequences of this. And then we will have a number of applications where vibrations are needed, in particular in determining crystal structures at non-zero temperatures and pressures, how the vibrations help in doing so. And there will be a number of other applications where vibrations play a pivotal role, for instance, in determining transition rates. Okay, so let's start from introducing vibrations. So probably, I hope, you have learned from previous lectures about the adiabatic approximation. So I'll go through this really quickly. So we have a Hamiltonian of the system here, which consists of the electronic part, nuclear part, and the interaction between electrons and nuclei. Using this Hamiltonian, we solve the Schrödinger equation, where capital R determine here all the nuclear coordinates. So it's a big vector with all the nuclear coordinates, and the length of that vector would correspond to the number of degrees of freedom in our system. And little x corresponds to all electronic degrees of freedom, so positions of electrons and their spin. And here you see explicit expressions for these different components of the Hamiltonian. For example, for electrons, we have electronic kinetic energy, interaction between electrons. For nuclei, we have nuclear kinetic energy, interaction between nuclei, just Coulomb interaction. And electron-nuclear interaction is, again, a Coulomb term. Of course, this Schrödinger equation is rather complicated. So in order to solve it, one way of solving it is to solve it in steps. The first kind of step is to assume that atomic positions, nuclear positions, are fixed at some vector r, capital R, so it's a fixed position, and then consider electronic subsystem only in the field of this fixed nuclei. So you can see this is the electronic only Schrödinger equation, in which you have electronic kinetic energy of the electrons, repulsion between electrons, interaction of electrons with fixed nuclei, and nuclear term. Nuclear term with respect to the electronic degrees of freedom is, of course, a constant. But we still include it so that that eigenvalue of this Schrödinger equation would correspond to the total energy of the system, in which electrons are treated quantum mechanically and nuclei are treated classically. So this object is called potential energy surface, and it's very, very useful, as you will see in the following. This Schrödinger equation would give us not one, but many solutions, which are distinguished by this index theta, which correspond to the quantum numbers. So we will get a ground state of the system, as usual, for the given positions of the nuclei, at the first excited, the second excited, and so on, as many states as we're able to obtain. But so far, the nuclei were treated as fixed. And this is a good approximation, because mass of the electrons is much smaller than the mass of the nucleus, at least 3 orders of magnitude smaller, and therefore you can assume that whatever nuclei move, electrons just follow as a cloud. Of course, this approximation is not always valid. I think I will have a few words to say about this, but not much. If we really want to be more precise, we would need to mix these different wave functions corresponding to the ground and excited states, and that can be done by considering this linear combination. Of course, these functions form a complete set because they are obtained by solving an eigenvector problem with this operator here, and therefore the total wave function, exact wave function, can be expanded into them, and the coefficients of the expansion would be functions only of the nuclear positions, and this would correspond to a kind of physically to nuclear wave functions. So in exact non-adiabatic approximation, non-adiabatic treatment, not approximation, the total wave function is given by this linear combination with respect to all electrons only wave functions with fixed nuclei. But in the adiabatic approximation, we take just one term in this expansion. So we remove the sum and consider the total wave function as a product of the electronic only wave function and the nuclear only wave function. So this is the idea of the diabatic approximation. Of course, instead of the equal sign, I would rather put approximate here. And one can, in this kind of ansatz, one can write equations these functions must satisfy, but which we are not going to write here. But in the adiabatic approximation, these equations have this form, and then again they look like a Schrödinger equation, in which you have kinetic energy of nuclei and something here which serves the potential energy, and that potential energy includes this potential energy surface term, which is the eigenvalue of the electron only problem. But there is also another term which is sometimes not is weakly dependent on the nuclear positions. So we will treat the sum of these two terms as the potential energy of the nuclear, which is available to us from some other calculations, for example, by solving this equation for different positions of the nuclei. For different values of capital R here, we are able to solve it. If you run, let's say, for example, a DFT calculation for different nuclear positions, you would be able to determine this quantity approximately, of course. When this approximation of a single term in the sum is a good one, this is when these energies here of the electronic only problem as functions of the nuclear positions are separated from each other. So this is the ground state. So this zeta index equal to 0. This would be the first excited state, zeta index equal to 1, and so on. So if the separation between these parabolas are large, then their contribution into the wave function for this range of nuclear positions, when this separation is large, would be sufficient, this single term. If, however, you have these parabolas intersecting, like in this picture, in that region, that approximation would fail, and you will need to include more terms. For example, you will have to include the term associated with this parabola and with this parabola in this linear combination, and this would correspond to non-adiabatic approximation. Another way of looking at this is as follows. When we have these parabolas here, we can solve this equation, and of course, because these are parabolas, so this potential energy in this Schrödinger equation is harmonic, we would expect the solution of that equation would give us energies of the harmonic oscillators, and these energies would be added to the total energy of the electrons, and therefore you will take the energy of the electrons and the minimum of the potential energy surface plus energies of these harmonic oscillators, which would go up like this. You remember, for a single harmonic oscillator, the energy is like that, where n is the why it disappeared? Where n is the quantum number. Yes, but you may have here not one but many harmonic oscillators, so you have a sum over these different harmonic oscillators, and this would give you these discrete energy levels, which would fill up this parabola from the bottom to the top. So if we have many phonons, we can fill in between the minima of the two neighboring parabolas, then the contribution from this other parabola may be neglected. If, however, these parabolas are very close to each other, so not many phonons can be fit in between the two minima, then this adiabatic approximation would not work. So this is basically what I just said, mathematically expressed like that. So the characteristic phonon energy divided by the difference between these two energies is much smaller than 1. So that means that that distance here is very small. You can may fit many phonons within this energy interval. So what can we learn from the potential energy surface? So as you understand, say example, if you run density functional calculations or quantum chemistry calculations, you can determine for the given positions of the nuclei the total energy of the system. And the total energy of the system, of course, would be different for different atomic positions. So you can basically map up the whole potential energy surface, how the total energy of the system depends on the positions of the nuclei. So what can we learn from this information alone? First of all, we can plot it. Of course, I can't do this for multi-dimensional potential energy surface, but for example, if I have a single degree of freedom, R, my energy would be something like that. So each minimum would correspond to a minimum of the potential energy surface. So if I have atomic positions being those in the minimum, that system would be stable. Of course, some minima would be of higher energy, some minima would be of lower energy, and there will be one with the lowest energy of all possible. That would be the ground state. All other minima would correspond to the metastable states. So we can learn about all stable states of the system, and in particular, we can see where the ground state of the system is. And in fact, if you consider a bucket ball C60, it has a very large number of such metastable minima, and just one very low ground state, the fundamental minimum, which corresponds to the bucket ball structure, the football kind of geometry of the 60 carbon atoms. What else we can learn? If we can map up not only minima, but the points around that this minima and the points connecting different minima, we can learn about the saddle points. And this is also important, as we will discuss probably next week. We can actually calculate from this information and also from the vibrational frequencies in each of these minima and around the saddle point, we can calculate the rates of transition from the metastable state to another state or backwards, which is also a very important piece of information if you are interested in studying kinetics. So we can calculate the barriers between the minimum and the saddle point. So if you're going from here to here, you would need that barrier here. If you're calculating the rate from here to here, you would need that barrier to be calculated. But also, as I said, you would need vibrational information as well, which would contribute to a prefactor of the transition rates within the transition state theory. Also, vibrations happen to appear in many other instances. For example, in thermal properties of the crystals or molecules, in the transition rates, as I said, in the prefactors, and in determining stability of the system. And we will consider some of this. But first, let us discuss quickly how would we go about solving the vibrational problem. And as I said before, we will consider a classical approach first, because in many cases, nuclei can be considered in a classical approximation. So basically, that means that we consider only the electronic problem and only consider the potential energy surface, which coming out as the eigenvalue of this electronic only problem as a function of nuclear positions. So we will not be considering solving this equation, nuclear equation, quantum mechanically as yet, but we will do this at some point later on. So if we assume that atoms oscillate around their equilibrium positions just a little, which implies that the temperature is not too high, then these displacements are very small. So this is a displacement of, this is a position of atom A, Cartesian coordinate alpha, and this is equilibrium position of the same degree of freedom. So the difference between these two is the displacement. So we consider these displacements to be small. Then we can expand the total energy of the system, or the potential energy of the system, that term which serves as the potential energy in the Schrödinger equation for the nuclei. But now I consider this classically entirely. We can expand it into these atomic displacements, and of course there will be zero or AE naught term with a zero corresponding to the zero displacements, or the minimum of these parabolas. Then there will be a linear term, quadratic term, and so on. The linear term is equal to zero because the first derivative of the energy with respect to atomic positions calculated at equilibrium, this zero superscript corresponds to that, of course, is equal to zero because this is equilibrium, this is the minimum of the potential energy surface. So that term is zero. So the first non-zero term with respect to displacements is a quadratic term. And the coefficients to these displacements is a Hessian second order derivative of the energy with the potential energy with respect to the atomic positions, with respect to all the degrees of freedom. It forms a square symmetric matrix, which is called force constant matrix. And this matrix determines the vibrations. So basically, the energy of the system is the energy at the minimum of the potential energy surface plus contribution to the vibrations. And in the harmonic approximation, when we disregard all the higher order terms and consider only the first non-zero term, which is quadratic term, in the harmonic approximation, we have parabolas. We have paraboloids, if you like, in the multidimensional space of that energy as a function of different displacements of the system. Yeah. It is useful to have in mind a picture which is shown here on the slide. How do we treat vibrations classically, quantum mechanically? Even though quantum mechanical description will be postponed, I will mention this now. So in a classical picture, we have the total energy of the system, E, as the function of atomic positions, being some sort of a parabola. And we imagine atoms, when they oscillate, the energy changes according to this parabola. So we can assume that atoms, okay, imagine that atoms kind of go around that parabola when they oscillate. In the quantum mechanical case, this is not the case. We don't have atoms treated classically, so they do not move attached with a spring with each other. Instead, we consider the energy in the minimum of these potential energy surfaces and at vibrational quanta, as I mentioned before. So these are two different pictures, and the higher the temperature in the classical picture, you would imagine the amplitude of the atoms becomes larger and larger, so they go more and more on this parabola. In the quantum case, we simply have more and more oscillators, and that corresponds to reaching higher values of the energy on that parabola as well, but using a different means. If you have questions at any point, please do not hesitate to ask. Just make yourself unmuted and just ask. All right. Okay. So before we come to the solution of this problem of finding vibrations, let's consider a few properties of this force constant matrix, which appears in the expansion of the energy with respect to atomic displacement. So I use here indices ij, which are composed indices for the degrees of freedom. And obviously this matrix is symmetric because it should not depend on the order of the indices I and j, yes, because we have this quadratic form, symmetric. So we have that expression. Also, you can establish a number of properties this force constant matrix must satisfy. First of all, let's have a look at the force acting on degree of freedom of J. This can be obtained by taking a derivative of the total energy with respect to displacement of that degree of freedom. So if you take this energy and differentiate with respect to displacement with the minus sign, you will arrive at that expression here. So it's a linear combination of atomic displacements, with the coefficients being a row or column, depending of the force constant matrix. Now imagine that all displacements are the same and equal to v, some vector. That means that the whole system is displaced, translated as a whole. In that case, if you look at the force from that formula, you can take these displacements, which are all equal to this vector v, out of the sum, and you arrive at that. And of course, there will be no force. If all atoms are at equilibrium, that displacement, when all atoms are displaced by the same amount, would not change anything. So there will be no force due to this translation of the whole system. And therefore, that expression here in the sum must be equal to 0. So this is a general form of a constraint for this matrix, force constant matrix. You can also consider rotations of the whole system, and again by the same vector around a certain axis, and derive an analogous constraint on that force constant matrix because of the rotations. Of course, if you rotate the system as a whole, all atoms rotated on the same angle. By the same angle, there will be no net forces due to that, and therefore there will be similarly a constraint. For periodic systems, there are some additional symmetry properties this force constant matrix must satisfy. First of all, in the crystal, you have unit cells which are periodically repeated, and the position of every unit cell can be specified by a proper translation L. I will use for translation this capital L. So capital L will give us a translation vector which points to the particular unit cell of interest. Inside that unit cell, you may have several atoms. So different atoms within a unit cell, we will designate by the index S. And of course, we also need a special index for the Cartesian degrees of freedom, because a displacement is a three-dimensional vector. So for that, we will use index alpha. So each index ij over the degree of freedom is given, in fact, by three indices, L, S, and alpha, in the periodic system. What I'm going to show to you now is that the force constant matrix would depend only on the difference of these two vectors. So force constant matrix has two indices, I and J. So because I and J are composed of these three indices L, S, alpha, you may assume that F would be indexed by L, S, alpha, L prime, S prime, alpha prime. But in fact, because of the periodicity, it is not indexed independently by L and L prime, only by their difference. And that can be demonstrated in the following way. Let's consider a crystal with all atoms at equilibrium positions. And let's take one unit cell L, one atom S in it and a displacement in the direction alpha, and only one single displacement is non-zero. All other displacements are zero. So we displace only that particular atom S in the unit cell L and along the direction alpha. In that case, out of all this sum, we will have only one non-zero term. Of course, in the matrix phi, would have L and L, two indices of the same unit cell appearing here, yes? But of course, the energy would be the same if you displace atom S along the direction alpha in the unit cell L or in unit cell L prime. Because of the periodicity of the system, that should not be different in any way. Therefore, that matrix must not depend on the L. So these two indices, when they're the same, makes this matrix not depending on them at all. All right, and this corresponds to that picture, because if L and L prime are the same, that index is zero. So there is no dependence on L at all. Similarly, you can displace two atoms, one in the cell L, atom S, and then atom S prime in the same cell, but different atoms. In that case, you will have two contributions to the energy. And again, you will find that these two indices being the same would not lead to any change. And similarly, then you can consider two atoms, S and S prime, but displaced in different unit cells, L and L prime. And again, when you have two atoms, one in L, one in L prime, look at my picture, you will get some energy difference. But if you shift the whole thing by some translation, that should not depend, the energy difference should not depend on that. And therefore, that result which you obtain would contain three terms. One due to displacement of atom in cell L, another due to displacement of an atom in the cell L prime, and one due to both displacements. But we already discovered that these two terms separately should not depend on the indices L and L prime. Therefore, that term should not depend on them on L and prime separately. It may only depend on their difference, because the difference is their relative positions with respect to each other. You see? So, so this simple analysis shows that for periodic systems, the force constant matrix may only depend on the difference of the lattice vectors associated with two unit cells, not on each of them separately. Now we can quickly look at how one can determine all the displacements in the multi-dimensional system. Of course, one-dimensional systems you must have considered in your quantum mechanics course, or maybe on mechanics, but a multi-dimensional system is not really very much different. First of all, if we have a system Hamiltonian, this is kinetic energy, this is the potential energy and the harmonic approximation. We can calculate the force acting on the degree of freedom k by differentiating this potential energy with the minus sign. You get this linear term, as I already explained, and therefore you arrive at these equations of motion for all degrees of freedom. We can rewrite these equations of motion in the matrix form by introducing the matrix M of atomic matrix masses, diagonal, vector U of atomic displacement, and matrix phi, quadratic matrix of force constant matrix, and then these equations would be in the matrix form look like this. And in order to solve them, what we shall do is to rescale the mass, the displacement by masses. So we will introduce a matrix M1/2, which is the same diagonal matrix, but with the square root of the masses appearing along the diagonal. And so with this new this rescale displacement V, these equations of motion would look like that, where matrix D is rescaled force constant matrix by atomic masses. So this will appear in the power -1/2 when we have 1 over square root of mass along the diagonal in each term. And this matrix D would have that structure. This is called dynamical matrix. And this equation, it looks like an equation for the harmonic oscillator. Indeed, look at this. If I take this dV term to the left-hand side, it looks like a harmonic oscillator equation with a D being square of the frequency. But don't be fooled by this, because by this analogy, because V is a vector and D is a matrix. It's not quite the same. But of course, when you have a one-dimensional system, this will be a harmonic oscillator equation. But we can use this analogy actually to solve this equation by assuming that this vector V here, which obviously depends on time, its time dependence can be described by this complex exponential, as would have been the case if it was a one-dimensional system. And the vector Y would be a constant vector of the same dimension, of course, as the vector V. So we assume that the vector V is a vector, constant vector, times this scalar complex exponential. And if we take this trial solution and substitute in here, we will see that the exponential factor cancels out. So we guessed correctly the time dependence of our solution, and we arrive at this equation for the unknown vector Y and unknown frequency omega, which we used here in the exponential term. And this is nothing but the eigenvector eigenvalue equation. So you can see that these vectors Y, which appear as prefactors to the solution, and are eigenvectors of the dynamical matrix, and omega squares, these are eigenvalues corresponding to the particular eigenvalue of the dynamical matrix as well. And if we now recall that actual displacements are related to the rescaled displacement, why this m in the power 1/2, we can write for each eigenvalue an eigenvector, which I will designate with the index lambda. We can write this expression. So this is the solution of the vibrational problem corresponding to the type of the vibration lambda with the frequency omega lambda and the eigenvector y lambda. So a full solution of the problem will be a linear combination of this. This is a classical kind of picture. So full solution of this set of equations, or this set of equations, would be a linear combination of these solutions, elementary solutions, and the coefficients in that linear combination must be obtained from the initial conditions. So this is how this problem is solved classically. There is a better treatment, if you like, of that problem, but I will probably skip this because we're probably running out of time. Let's consider the potential energy of the system now. The potential energy of the system, this is that quadratic form we came about before. But if you now, as you know from mathematics, a quadratic form like this can be diagonalized. And that solution we obtain actually diagonalizes this quadratic form. This can be seen here. So if I write this energy using matrices, so this UT is a transposed matrix or transposed vector of atomic displacement. So it's a vector rho. Phi is the force constant matrix, and U is the vector column of the atomic displacements. Then what I can do, I can replace this phi with a dynamical matrix. Then this masses in the power 1/2 appear. Then this matrix I can combine with this U. This matrix I can combine with that U as shown here. And then I can write D in the so-called spectral representation. Why its eigenvalues and eigenvectors. Just remember, omega squares are eigenvalues of the matrix D, and Y lambda are its eigenvector. So I can always write matrix in that form. And if I plug this in here instead of the D, and again collect terms, I will arrive at something like that. And there will be a sum over all eigenstates of my dynamical matrix. Omega square would appear as a parameter, and here I will have two scalars, y lambda and y lambda, and these are exactly the same as we obtained here. So this with the u, with this being this time-dependent solution of a single harmonic oscillator. If you would like to see more in detail that, you have to follow these two slides. And I think there is a video of that from the previous lectures last year, the year before that, where I actually went through this. Or maybe you can just look at these slides. These slides will be available to you. It is shown that the full solution of that equations can be actually written like this, where these are eigenvectors and these y lambda are just solutions of a single harmonic oscillator equation. So these are little y lambdas which appear here. These are two scalars, and therefore we have them squared. So what we learned from this, that the potential energy of the system can be, why an appropriate linear transformation can be written as a sum over independent harmonic oscillators. And these y lambda correspond to monatomic displacements, if you like, when all atoms are displaced in some way together. And the coefficients are these frequencies. So we can easily analyze this expression now. For instance, suppose we consider a minimum on the potential energy surface. So we are here, and we expand our energy with respect to displacements from that minimum position. In that case, the dynamical matrix would be positive definite, and all its eigenvalues, omega squared, would be positive numbers. Therefore, this expression would contain this y lambda squared with positive coefficients. What that means? That means that if you displace atoms from their equilibrium positions, so you make this y lambda non-zero, this will always bring the increase of the energy, because the coefficients omega square are positive. Yes, so that means that indeed, if all omega squares are positive, remember that that omega squares are eigenvalues of the dynamical matrix D. Dynamical matrix is symmetric matrix, and from mathematics you should know that if the matrix is symmetric, we are guaranteed that its eigenvalues are real. However, we're not guaranteed these eigenvectors are necessarily positive, but if they're all of them positive, then we are guaranteed that any displacements of our system from the equilibrium position would result in the increase of the energy, which means we are at the minimum of the potential energy surface. But let's assume then that one eigenvalue is negative. So there exists an eigenvalue which is negative. That corresponds to the system being unstable. So if all other eigenvalues are positive, but just one are negative, our energy expression would look something like that. It would be minus 1/2 that negative 1 squared y squared for this negative degree of freedom, plus all other lambdas without that 1/2 omega lambda square y lambda square, which means that if we display our system along any other degree of freedom, not this one, but any other, we will always have the system energy increasing. However, if we display our system along that unfortunate degree of freedom, we will have energy going down. So there is a direction in the potential energy surface in which a certain displacement would reduce the energy, but in all other directions, the energy is increasing. It's a saddle. So this point would be a saddle point. And that point appears when we go from one minimal to the other minimum. So you will go from one minimum to the other minimum via that saddle point. That's why it's very important to be able to determine where saddle points are, because this would provide you with the important information about the transition rates from one minimum to the other. There's also possible that all these frequencies are positive. However, there are some frequencies which are very, very small. That means that along the direction associated with those frequencies, the potential energy would increase very, very little when you displace atoms quite significantly. That means that that minimum is a shallow one. And in this case, you have so-called soft mode. When a small increase of the temperature, for instance, may make this potential energy state unstable. The system would be able to move from here to another states which are lower in energy. Now I have a few slides on finite systems, which would give you some idea how vibrations can be determined for finite systems, such as molecules. And then we will consider a few examples of a crystal. So let's have about 10 minutes of these finite systems, and then we'll have a small break. Okay, finite system. I don't know if you know about relation to the interrelation between the symmetry and the conservation laws, but maybe you know that because of the translational invariance, you have the conservation of the momentum. Momentum of the system is the sum of momentum of each atom. So this dot corresponds to the time derivative. So if the momentum is conserved, that means that that quantity is equal to 0 or equal to a constant. We can always use it, choose it as equal to 0 if we choose the center of the coordinate system in the center of mass. So there are three equations for the with alpha equal x, y, and z, generally for three components of the momentum. There's also rotational invariance. If you consider a momentum of the system, which should be conserved as well. So momentum of the system is given by a vector product of the atomic position and its velocity, which is u dot, and we sum over all atoms of the system. If we now take this atomic position as the equilibrium position plus the displacement, and assume the displacements are small, so that cross product of u and u dot we can neglect, then we arrive at that expression where you have rho r equilibrium here, equilibrium position, and u dot, and again you can take d over dt out of this, and you see that that quantity must be a constant, which you can set to 0. So we have this expression here. So we have 6 equations. 3 equations coming from the translational invariance, 3 equations coming from the rotational invariance, and these displacements, so the displacements of our atoms when our atoms vibrate are constrained by this, because we have to eliminate these translations and rotations when we consider vibrations of the system. So generally for the for nonlinear molecule, we have 3 and minus 6 degrees of freedom associated with vibrations. And any vibrations we consider must not include this translational component or rotational component. For a linear molecule, there will be 1 degree of freedom less, 3 and more for the vibration, 3 and minus 5 altogether. So how does this work in practice? Let's consider a linear molecule. Very simple linear molecule here with 3 atoms. So 1 atom in the center, say, has a higher mass, and 2 lighter atoms on the left and on the right. The potential energy of my system I can write like this, where x, 3, 2, and 1 are the displacements of these 3 atoms numbered 1, 2, and 3. Yeah, 1, 2, and 3. So now I need to write these constraints for the displacements to eliminate them. How would I do this? For this one-dimensional system, that translational invariance would correspond to a single equation like this one. And of course, the system is one-dimensional, so we don't have rotational constraints. So from this equation, you can see that displacements x1 and x3 and x2 are constrained. They are related to each other. So we have 1 degree of freedom less. We can, for instance, choose x2 to be eliminated. And in order to do this, we can introduce 2 new degrees of freedom, 2 new coordinates, generalized coordinates, QA and QB, like this: Q1 and Q plus Q3, and X1 plus X3 and X1 minus X3. And remember, X2 we eliminated, therefore X1 and X3 become independent. But instead of choosing them as our coordinates, we chose the linear combinations X1 plus X3 and X1 minus X3 as our new degrees of freedom. Using these 2 equations and that equation, you can determine the 3 coordinates like this. Why are the new degrees of freedom QA and QB? You see, all 3 coordinates are nicely determined from the 2 coordinates. Give me 1 second. I'll need to change my pen. Okay, so once we've done this, we can rewrite kinetic and potential energy via these new coordinates, right? So we write this via the new coordinates. So we have x1, x2, x3 via these q coordinates. So we can easily rewrite kinetic energy as written here, and the potential energy. And you see, these 2 coordinates are sufficient to write both kinetic and potential energy, as one would expect, because 1 degree of freedom is really redundant. So we can write the full Hamiltonian as a sum of the kinetic and potential energy. And you see that the Hamiltonian has a sum of 2 contributions, and they seem to be completely independent of each other. So once we have, because one Hamiltonian contains QA and then the other Hamiltonian contains only QB. So we actually decompose the whole system of oscillators into 2 independent harmonic oscillators, and by solving these 2, we can determine their vibrational frequencies. And then once we know these vibrational frequencies, we can actually have a look what happens to the atomic displacements when we excite just 1 vibration. For instance, let's excite just QA. So QB is 0. So when we excite QA, x1, so suppose QA is positive, x1 goes in the positive direction, x3 goes in the same positive direction, but x2 goes into the negative direction. And you see, this would be that mode. So atom 3 goes to the right, atom 1 goes to the right, but atom 2 in the center goes to the left. And of course, the magnitude at which this atom 2 goes to the left depends on the ratio of these 2 masses. If instead you consider exciting QB, this other mode, then QA is 0, then x2 doesn't move, x2 stays the same, but x1 and x3 have opposite signs. So in this case, atoms oscillate like this. So in the mode B, atoms oscillate like this, and the central atom doesn't move. But in mode A, you have this kind of oscillation, but this blue atom moves in one direction, and the yellow atom moves in the other direction. Now, let's consider a little bit more complicated example, but I will consider it just qualitatively for you. If you would like to go through the whole solution, I think I uploaded the full solution of that water molecule problem on the TYC website. But the idea is this. So we have, in this case, we consider the vibrations of the water molecule as a 2-dimensional problem. We have 2 translational invariance conditions for the x and y directions written here. And we have a 1 rotation, just 1 rotational degree of freedom. As this molecule rotates in the XY plane. And therefore, there will be only one condition, which can be written like this. So you can see out of how many degrees of freedom we have. So each atom, this hydrogen atom, would have 2 degrees of freedom, X and Y coordinates, 4. And the oxygen in the middle would also have 2, so 6 degrees of freedom. But we have 3 conditions, 2 translational and 1 rotational, so 3 degrees of freedom out. So we are left with only 3 degrees of freedom for the vibrations. So then, following the linear molecule example, we introduce new degrees of new coordinates, QA, QS2, and QS1, using these notations. And using those and the 3 constraints we have, we can express coordinates X and Y of each atom exclusively via these new Q coordinates. So which shows that these 3 coordinates are actually sufficient to describe vibrations of the molecule, because we need just 3 coordinates, and we have 3 coordinates, and every coordinate of our original 6 coordinates can be expressed via this. Then it comes a rather tedious part of rewriting kinetic and the potential energy of the molecule via these new Q coordinates. And for that, we need to assume that the displacements of atoms when they vibrate are very small, which means that the distance L between these hydrogen and oxygen atoms and this one, they change a little. And also that angle alpha changes a little. This angle alpha corresponds to the molecule moving like this, right? So it changes very little. And then you can actually approximately work out, using a Taylor expansion, the change of these distances 1, 2, 1, 2, and 2, 3, this one, and also of the angle alpha, express it linearly via these displacements x1, x2, x3, y1, y2, y3 of our atoms. And once you've done this, you would be able to write the potential and the kinetic energy of our system. Okay, when we write the potential energy of the system, we assume this following form. So we have some stretching contributions in the form of a harmonic oscillator, each of them, and some contribution due to the change of the angle between the hydrogens and the oxygen. Of course, these elastic constants, K1 and K2, should come out from somewhere, either from some force constant, classical force constant model, or maybe from some quantum mechanical calculations like DFT calculations. So if we assume that this constant K1 and K2 are known, are given, then we can replace these changes of the distances and the angle and into here, using these expressions for them, and then replace atomic positions, atomic coordinates x, y for each atom, y the q coordinates. Again, a rather cumbersome calculation, but rather simple. And if you do this, you will see that potential energy can be given by the sum of these 4 terms here. Similarly, you can consider the kinetic energy as well. This would be kinetic energy of atom 1, or to atom 3, and of atom 2. And again, you substitute them via the q coordinates, and you will have that expression. Then we will construct the Lagrangian, or if you like, you can construct the Hamiltonian, and you write equations of motion. Again, if you're not familiar with the Lagrangian formalism or Hamiltonian formalism of classical mechanics, this is not a problem. The point here is that one can determine, one can express the potential energy, kinetic energy of the water molecule by these 3 q coordinates. And when you do this, you will find that the potential energy expression for the QA coordinate and the kinetic energy expression for the QA coordinate are completely independent. And therefore, they form a degree of freedom which are independent of other 2 degrees of freedom, QS1 and QS2. And therefore, if you sum these 2, you will get simply an energy of the harmonic oscillator. And this will be the frequency of the harmonic oscillator. However, if you consider QS1 and QS2, they actually coupled to each other, because in potential energy term, you have this term where these two coupled. Kinetic energies doesn't have them coupled, they're uncoupled, but still they're coupled, and therefore when you solve the equations of motion for these two other coordinates, you will have to solve these two simultaneous differential equations, and if you do this, you will obtain two eigenvalues. This will be omega squares for these 2 degrees of freedom, and 2 eigenvectors corresponding to them y. I'm using now notations which I used previously. And for the omegas, you will have this rather interesting fourth order algebraic equation. So of course, for omega square, this would be a quadratic equation which you can solve, and you will get 2 solutions. And similarly to what we did for the linear molecule, we can, as I said before, we can express x and y coordinates via these q coordinates, and then these 2 q coordinates, of course, they form eigenvector. So so from here, so you will have 2 eigenvectors. You can set one eigenvector to 0 and use another eigenvector, which would mean that you excite just 1 degree of freedom, you do not excite the other. So in that case, you will have kind of one mode with one frequency. This oscillates like this, so the water molecule goes like this, and another degree of freedom is like this. So you have stretching or compression of this hydrogen-oxygen bond, and oxygen just moves up and down by a little because oxygen mass is much larger. The other mode in which this QA only excited, this corresponds to this rather different vibration. So you have hydrogen moving towards the oxygen, one hydrogen, and another hydrogen moving away from oxygen, and depending on which one goes in, which one goes out, the oxygen moves either to the left or to the right. So these are 3 vibrational modes of a water molecule. So this would give you full solution for the water molecule, and what you need from, say, DFT is to only determine these coefficients, and then you can determine from these equations all the frequencies of the water molecule, vibrational frequencies. Here I give you one approximation to the water molecule potential energy surface with all the constants. So you have Kr here in units eV and angstrom. You have this K theta for this angle term here, but you also have some other terms which are much smaller but give a little bit more precision, if you like. So there's a kind of hybrid term between two HO distances, elongation and delta alpha term, but these are much smaller. But still, even in that case, the whole calculation can be repeated. Of course, it will be much more cumbersome, but this is what you can do. All right, so before we go into crystals, I suggest we will have a 5-minute break. Unless you have some questions to ask now. Any questions? So if not, let's go for a 5-minute break, okay? Okay, I'm back. So, can we continue? Everybody is in?
Give it like 1 or 2 minutes.
Yeah? We can move on, yeah? Why is not? Okay, to minimize. Okay, okay, good, excellent. Thank you for the thumb up. Right. So these were molecules. So about the molecules, if you're interested in finding vibrations for molecules, you need to remember that you have to eliminate the translational and rotational degrees of freedom. And maybe some of the codes would do this for you. Some maybe not, but you have to find out, yes? And now let's consider crystals. As we discussed before, in the case of crystals, we have a degree of freedom. Can you see my cursor, by the way? I didn't ask.
Yes.
Yes, okay, perfect, because my pen is killed, is down, dead. So any degree of freedom in a crystal is given by this triple index. L identifies the unit cell, S atom within that unit cell, and alpha the position. And if we write now equations of motion for, sorry, not equation, but the eigen problem for the dynamical matrix D, remember we have the dy equal omega square y. Now, if we write this explicitly, it would look like this. And the matrix D would appear as with the indices L and L prime in the difference, as I explained before. Of course, you will have to introduce so-called Born-von Karman boundary conditions. For one-dimensional system, this simply corresponds to having a ring. So we have a chain of atoms from 1 to n, but the atom 1 is basically the same as the n plus 1th atom. So atom 1 is surrounded by exactly the same atoms on the left and on the right. So in the 3 dimensions, this kind of ring idea doesn't work. So what you need to do is to introduce a very large unit cell with the n1 atoms in one direction, n2 in another, capital N3 in the third direction, and that thing would be then repeated. So any displacements of atoms within that cell would be huge cell. I should say this n1 and 2 and 3 are really assumed to be macroscopic. So any displacements of atoms within that huge cell would be repeated in all 3 directions. Yes. So if you look at the atom which is next to this, maybe my pen can work actually. If you look at the atom, so if you consider this atom, oh no, not yet. If you consider this atom, so next to it will be atom here. This would be the same as atom this one. Yes. So this is the idea of these periodic boundary conditions. And because of these periodic boundary conditions, we can write the displacements in each direction along the lattice translations A1, A2, A3. These are primitive basic lattice translations. They would repeat themselves. So only translations, only displacements within the box, this big box, would be different. But if you go across the box, they would repeat themselves. And these conditions actually impose some important constraints on the possible vectors k, which can number different solutions of this equation. So if we take a particular vector k and apply this sum to this equation, so we basically would sum over, you see, here we have already sum over L prime, but let's sum on the left over L and on the right over L, but also introducing this complex exponent. So if you do the math here, then you will find that you will arrive at this colored equation. So the matrix D depends only on the difference of these vectors. So you can introduce here a vector L double prime proper translation, which is a difference of L and L prime. So this would kill one sum. Another sum would appear here, L prime sum. And also a similar sum would appear in the right-hand side. So what this transformation gives us is that for any k, one can introduce this object as a linear combination of these atomic displacements. Instead of the matrix D in the side representation, introduce this largest sum, again with some k. This object here, this dynamical matrix, would not longer depend on the largest translations at all, because you see this index L double prime is summed over. So this matrix would, however, this yellow matrix would depend on the vector k. So for each vector k, that whole object would only be indexed with the indices S and alpha. S and alpha, these are two indices which run only over the degrees of freedom within the unit cell. For example, primitive unit cell or some extended unit cell. So this is a finite matrix then, D. Yeah. So if you have, say, one atom in the primitive unit cell, you consider largest translations in the primitive unit cell with respect to the primitive unit cell, you will have this matrix being 3 by 3 only. If you have two atoms in the primitive unit cell, there will be 6 by 6 matrix. But for each index k, you will have this matrix. So of course, the overall dimensionality would be still the same as before, because you will have many k vectors to consider. Also, so this is the matrix D as a linear combination with respect to largest translations for different vectors k. And this is that displacement, again, in the reciprocal space now, is also for each vector k, this will be a finite dimension, a vector of finite dimensionality. Again, if you have one atom in the primitive cell, there will be just 3 components. If you have 2 atoms, there will be 6 components. And that will be given by this lattice expansion, similar to this one. And now you can notice that not all vectors k actually would contribute. So because of this translation invariance associated with the Born-Common binary condition, but cyclic boundary conditions, only vectors k within the first Brillouin zone would actually give different solutions. Vectors beyond the Brillouin zone would make this exponential being still the same. So every vector k, now I have to write somehow, but I can't because my pen is still not working. You see, maybe, it started working. Good. So any vector k with the in the reciprocal space, let's call it capital K, can be always written as reciprocal lattice vector, proper reciprocal lattice vector, and the vector little k from the Brillouin zone. So if we now substitute this vector k instead of this k here, you will see that e to the igl would give 1. So this exponential for any vector k with a g would be the same as with the vector little k of the first Brillouin zone, which means that we have adding to the little k here of the first Brillouin zone, any reciprocal lattice vector would not change anything. So little vectors k, which number all the solutions, are only constrained within the first Brillouin zone. That's the message here, because of these periodic boundary conditions. So in order to solve the 3-dimensional vibrational problem, what we need to do, we need to determine matrices D or dynamical matrix in the real space, then sum them up over these lattice vectors for each vector k within the first Brillouin zone, get them. These are final dimensional matrices for each vector k, and then solve for them this eigenvector problem for each vector k. That would give us the required solutions. I have here an example, but you may probably have this had this in your courses, undergraduate courses, just a simple monatomic chain of atoms, which you can solve. You can determine these displacements and vibrational frequencies. You can also consider a diatomic chain at the bottom here, which would also give you this time two solutions. If for the monatomic chain, you will only obtain acoustic branches, so you will obtain the omegas, which starts from 0 and go up as k is going from 0 up. But in the diatomic chain, you will actually have two branches of vibrations. One, which starts from 0, when k goes from 0 away from 0, and it starts from a finite frequency when k goes away from this 0 value. So here, when omega changes, starts from 0, we have acoustic branch, and omega is proportional to the k, and this corresponds to acoustic waves. When k is very small, the wavelength of the vibrations is very large, which means that atoms in the vicinity of each other oscillate in concert together, right? But for that mode, one can show that eigenvectors of this mode are such that if atoms vibrate around here in the vicinity of k equals 0, they actually vibrate in opposite directions, not in concert with each other. So this is called optical mode, because if these atoms were oppositely charged, they would create an oscillated dipole moment, which would interact strongly with electromagnetic waves. That's why it's called optical. So in a crystal with 3n atoms, in a crystal with n atoms in the unit cell, in the primitive unit cell, so there will be 3n degrees of freedom. You would have always 3 acoustic branches, which start from 0, and at small k, vibrational frequency would depend linearly on k. So this would correspond to 3 acoustic waves. And the rest of the branches, there must be 3n branches in total. The rest of the branches would correspond to optical modes. For if you have a single atom in the primitive unit cell, for example, simple metals like copper, lithium, sodium, they form FCC lattice with a single atom in the unit cell. You have just 3 acoustic branches. But if you consider MgO, for instance, it's again FCC lattice, but with 2 atoms in the primitive unit cell, you will have 3 acoustic branches and 3 optical branches. If you know interactions between pairs of atoms and you consider an approximation of central forces, when the potential energy of the whole system is composed as a sum of all pairwise interactions, and each pairwise interaction, it only depends on the distance between atoms, one can actually analytically calculate the force constant matrix, and it would look like this. It will automatically depend only on the difference of the lattice vector. So the whole calculation is on this slide. It's just an example of how one can determine this analytically if there is a need for that. But how can we do this from ab initio calculations? So I now going to show you a number of ways of how this can be done, and maybe next week I will show you a bit more on this. So suppose you can run DFT calculations and you would like to determine the vibrational frequencies of the system, or how atoms are vibrating. One method is called frozen phonon approximations. So what that means? So suppose you have a system here. Let's, for simplicity, consider molecules. And you would like to determine all the vibrations of that molecule. What would you do? You can displace the atom A, say in the positive direction, say along the x-axis in the positive direction, and then you can displace it in the negative direction. You can displace it along the y. Or the point is that if you displace this atom along a single direction So there will be just one displacement to consider. Then the force, if you remember the force on any other atom due to that kind of displacement is given by this formula. I can return back to our energy expression and the force, just to remind you this expression. It is was somewhere. We did consider that. No. Where was it? Here we go. That expression here for the force. You see, it's a linear combination of all displacements and the force constant matrix. So if we displace just one atom in the system, in that sum, what happened? Oh, that's a bit of a disaster, but let me try. My iPad died. I don't know what happened. It doesn't keep the charge at all. Give me a second. I will. Right. Okay, so we're here. All right. So this is the expression for the force. But if we displace just 1 degree of freedom, of course, of all of this sum, only one term will remain, right? Associated with the second index of that degree of freedom which we displaced. Now, if we displace this atom, we can run a calculation and calculate the forces on every atom of our system. So while we displace just 1 degree of freedom, we have the forces on all atoms of our system, including this atom. So that vector of forces is available to us. And this is a number, a displacement. For example, you can take 0.01 angstrom as a good displacement. You can't take too small displacement because in that case, if the displacement is very, very small, you will have very bad forces on atoms because of numerical instability. But you can't take a very large displacement either, because if you take a very large displacement, that formula breaks down because harmonic contributions to the energy start to play a role, and there will be terms in the force, quadratic in displacement. So there's some balance you have to take. But from experience, 0.01 angstrom, something like that, 0.005 angstrom, sometimes 5 thousandths of an angstrom is workable. So once you have this displacement, which is your displacement, you decide which atom you use, which along which direction you use, and what is displacement, and you obtain all these forces, for example, from DFT, and from that you can obtain this matrix using just this division. You can also displace the same atom, but in the opposite direction. Then you will have another set of forces. And by these two forces, you can determine this matrix again. And that would give you a better approximation for this. Of course, so by displacing the real freedom A alpha, you get all the components B beta of the matrix phi. So this way you will get a certain column of that matrix phi. Now you take another atom and you displace it, and you get another column of that matrix phi. So by displacing one by one all atoms of your system, you will be able to determine the whole matrix phi. Okay? But of course, that matrix must be symmetric, but because of numerical way in which this matrix is calculated, it won't be exactly symmetric. So you may want to symmetrize that matrix by taking, for example, average of the right and left triangular parts of the matrix. Now I need that other slide to show you. Let me see if I can connect my iPad again. Just 1 second. So we now need to discuss what is the interrelation between the primitive cell and extended cell, supercell, on the one hand in the direct space, and the brilliant zones in the reciprocal space correspondingly. Okay, no, it's not ready. I don't know what happened. It was fully charged. I'm sorry for this, guys. Karen, maybe stop recording for. Right. Okay. I've got the new file, so that's very good. Right. So let's have a look at this. So here on the left, I have a primitive cell. On the right, I have a case of the extended cell. So in the direct space, I have a simple square lattice with a primitive unit cell here. So A1 and A2 are two lattice translations, okay? And it's a square lattice, so the distance between atoms is A, just one atom in the unit cell for simplicity. Now, corresponding to this primitive cell, I have the brilliant zone in the reciprocal space, right? And that would be something like that, also a square, but the sides of the square will be 2 pi over that A here. All right. Now let's build a four-fold extension of this primitive unit cell. So this is my extended cell, so 4 times bigger, and these big vectors are big translations of my extended cell. And you can see that that big cell has small translations like this, which are not within these big translations, but are still proper translations from the point of view of my primitive cell. Yes. So if we have atoms here and here and here, these are all equivalent atoms, and here and here and here and here are all equivalent atoms. However, from the point of view of the extended cell, these are not equivalent. So we shall call these big translations of the extended cell, and these small translations, which still are proper translations of our lattice, we will call internal translations. So there's a view here that by extending cell, the unit cell, several number of times, you will remove some of the translations, because translations within that extended cell are not anymore considered as translations. But in fact, they are. And any translation of this lattice with the bigger cell taken as a periodic unit can be written as a big translation plus an internal translation. It's a similar analogy to the k vectors in the reciprocal space. I can't remember where I wrote this, when you can write any k vector in the reciprocal space as a proper reciprocal translation plus a vector k from the first brilliant zone. A similar analogy. All right, so if we have this extended cell, so we have these big translations and internal translations. The brilliant zone is actually a reduced brilliant zone. The brilliant zone is 4 times smaller. So before we had the brilliant zone like this, now we have a 4 times smaller brilliant zone here. The basic translations of the reciprocal space, this capital B1 and B2, are now halves of the previous B1, small B1 and B2 translations in the reciprocal space when we used a primitive cell in the direct space, right? So the brilliant zone is now smaller. And what we had before as vectors in the brilliant zone, these vectors corresponding to these red circles here, these were vectors within the first brilliant zone for the primitive lattice, right? And these were all independent. Now, with the reduced brilliant zone, these vectors are actually equivalent to the zero vector because they are connected to the zero vector by proper translations associated with the reciprocal, with the reduced brilliant zone. So we will come across this notion now here. So with the reduced brilliant zone associated with the extended cell, some of the vectors of the previously of the full brilliant zone becomes equivalent. to the 0 point. So these 3 points become equivalent to this point from the point of view of this reduced brilliance zone, because they're connected to this 0 point by proper translations of this denser reciprocal lattice. Okay, now, so this is my lattice in which I used a primitive unit cell. This is my lattice in which I used extended unit cell. And any translation in my original lattice can be written as a translation n capital of this big unit cell plus little n internal translations within it. So, for example, a translation from here to here, from here to here, from here to here. These are all internal translations. Okay, and as I said before, the brilliant zone associated with this lattice is this big one, and the brilliant zone associated with this lattice is that small one. All right. So now let's write the dynamical matrix for our lattice at the k point k with respect to the primitive unit cell. Sorry, no, with respect to the extended unit cell, actually. So this would be that lattice sum, and here L, we sum over L. No, I'm sorry again. This is with respect to the primitive unit cell. With respect to primitive unit cell. So we have this lattice sum, and the sum over L is composed of the translations with respect to the bigger cell and the internal translations. So that sum would become a sum over capital N and over small n. The sum over capital N is an infinite sum, but however, the sum over small n is the final sum. For example, in this case, this sum over n would contain only 4 terms: n equals 0, then n corresponding to this translation, n corresponding to this translation, and then corresponding to this diagonal translation. So it will be a finite number of terms. But L will be a sum of capital N and a small n. And of course, here will be n and small n, right? Okay, so let's now select this phi, the force constant matrix, with a part of that exponent corresponding to the capital N and the sum over capital N, my green term here, and leave only small n and the exponent associated with the small internal translation. And let's call this guy here little phi f, associated with the small translation. So we sum over all these big translations. If we knew this little f, right? If we knew them for the given k vector, we know all the internal translations. We know it is possible to determine all of them. If you expand from the primitive cell to the extended cell, you can determine these internal translations. There's no problem, as I explained to you on this example. Then you would be able to determine D by means of this finite sum over all internal translations, and then by diagonalizing this D, you would determine all the vibrational frequency associated with this k vector k. Fine. The question is how to determine this phi. So here comes a very simple trick. Let's look at this phi, which is given by that expression here. On the other hand, so that phi would need, in order to calculate that expression, we need to sum over capital N. For that, we need to have access to these phi matrices for all translations of the system, which is impossible. But for some specific k vectors, that sum can be obtained actually. So let us consider the following trick. We consider now an extended cell here, but we will displace only atoms within the primitive cell, which is a quarter of that big cell in my picture. So we will displace atom from the cell 0, atom number S1 in the direction alpha 1. So there will be just one displacement altogether. If we displace that atom by means of a density functional calculation, for instance, we can determine all forces on all atoms of our bigger cell. So that would be this. So we will determine all forces on atom S in all directions alpha for all internal translations n. So for all independent degrees of freedom associated with our extended cell. And that force, on the other hand, will be given by that expression. We came across this expression before, if you remember, when we considered this force constant matrix. This one. Oh. But this time, because we displaced just one atom, the sum of a capital N remains. And if you compare now this expression with this expression, you see that we would be able to get what we want if this exponential term would be equal to 1. So if you take k vectors such that this exponential term for every capital N, for every big translation, would be equal to 1, then we can determine in one go the whole expression is a square bracket, and that would coincide with this f for these vectors k, not for all k vectors, but only for those specific k vectors. So the question is, what are these k vectors, whether they exist or not in the first place, which would give that exponent equal to 1 for all possible big translations? And it is easy to see that such k vectors do exist. And these k vectors are actually a linear combination, arbitrary linear combination of the big translations in the reciprocal space. That smaller translations here, I call them big B, associated with the reduced brilliant zone. So if we take these big translations, then substituting this linear combination into that exponent here, you see this capital N is the linear combination of the large translations, capital A. And these two, they dot product, give 2 pi a Kronecker symbol. And these M and P's are integers. Therefore, we get 1. So what is the message from here? Is the following. So if we run a DFT calculation, for instance, for an extended unit cell, then we displace atom, say one atom, within the primitive unit cell in a particular direction, and determine forces on all atoms of our extended unit cell, we should be able to obtain that quantity here for all indices S alpha and for all index little n. So as before in the frozen for non-approximation, we will obtain a column of that whole matrix. So the column of that matrix with the given S prime alpha prime, but for all S alpha will be obtained. Now we take another atom and displace it, or the same atom but in a different direction, and you obtain another column of this. So for those k vectors which satisfy this condition, we can determine this full F matrix, and by summing this up over all internal translations, we can determine the dynamical matrix. So not for all k vectors, but only for those k vectors which are, from the point of view of a reduced Brillouin zone, are equivalent to the 0 vector, we can determine the dynamical matrix using this method. Okay. So this method is exact. There is no approximations whatsoever. So how does it work? So we take a certain extension of our unit cell. So little a's are primitive lattice translations. T is a 3x3 matrix, which provides us with the bigger translations, capital A. So we create this way an extended cell and determine all internal translations, little n. Then we determine all k points within the Brillouin zone which satisfy this equation. In other words, all points in the Brillouin zone which are equivalent to the gamma point of the Brillouin zone, k equals 0, within the reduced Brillouin zone picture. Then we displace atoms one by one in the primitive unit cell of the extended cell and calculate forces on atoms, and then calculate this little f. Once we have these little f's, We sum them up over all internal translations, and for those k points, we determine the dynamical matrix, diagonalize it, and we get omega as a function of that k point. You can play with the supercells. Of course, if you take a particular supercell, you have access in this way only to some specific Brillouin zones. For example, k points, sorry. For example, if the unit cell is a four-fold extension of the primitive, if your extended cell is a four-fold extension of the primitive cell, your Brillouin zone will shrink 4 times, and the reduced Brillouin zone will be 4 times smaller. So there will be exactly 4 points in the reduced Brillouin zone. So there will be 4 points in the full Brillouin zone, which are equivalent to k equals 0 of the reduced Brillouin zone. Yes? So in these 4 points, that kind of four-fold extension of the primitive cell in the real space, direct space, would give you frequencies. If you would like to have frequencies at some other k points, what you can do, you can try other extensions of the primitive cell. If you take an extension, not necessarily a symmetric one, some kind of weird extension, where this matrix T would not only have diagonal elements, but would have some off-diagonal elements as well, you will have access to some other k points. You will always have access to k equals 0, but you will have access to some other k points as well. So each time you created a new supercell, you have access to different k points. So by trying different k points and calculating forces by, as I explained, you have the access to the dynamical matrix at these k points. You can actually do something better. You can construct symmetry. You can construct displacements associated with a particular k point. So in order to reduce the number of calculations, DFT calculations, for instance, when you displace each atom in one direction, the other, you will have to run a DFT calculation still without relaxation, 1 point calculation. But still, if the system is large, this is a reasonably large calculation. So there's a way actually to consider displacements only associated with the k points of interest. So you took a particular extension, and you have k equals 0, k1, k2, k3, say, with that extension. You calculated these k points for frequencies for these k points. Then you took another extension of the primitive cell, and that cell is still big, but k equals 0. You have determined k equals 0 vibrational frequency already. So what you can do, and maybe there is another k point in this another cell, which you have already done. So what you can do, you can determine analytically. This is done in my tether code, for instance. You can determine analytically how to displace atoms in your primitive cells such that only that particular k point of interest, which is different from the previous k points you already determined the frequencies for, would be needed. All right. So there's a way to actually take a sequence of unit cells and extend them in certain ways, so to get access to different k points of your dynamical matrix. Of course, if you would like to draw a dispersion law, you would need k points not only also near the k equals 0. Maybe you will have many more k points. Then this method would not work. Because if you need access to the k points which are very close to 0, or k point which is very close to the existing k point somewhere inside the Brillouin zone, you will have to take a very large extensions, and then your extended cell will be so large that it won't be possible to run simulations for that one. In that case, other methods exist. Right. Like a perturbation theory, which I plan to consider next time. Still, you can determine with this method frequencies for a k point equals 0, the gamma point, and maybe points at the border of the Brillouin zone, and maybe some k points inside the Brillouin zone. And then you may do some interpolation. And the idea of the interpolation is this. So for the k points which are accessible to us with this method, we can write the dynamical matrix like this by definition. So we can determine this D, and from that equation, you can actually work out the elements by the reverse transformation, because this is just a Fourier series, right? By the reverse transformation, you can determine this matrix F for the internal translations, and that would be given by the sum over k points, which are reproduced by this method. Of course, this would be this would give you access to the force constant matrix only for a limited number of these translations here. Of course, the phi matrix depends on the difference. So you will have for n equals 0, so it will be a 0 vector, and there's few small vectors which are internal translations. You won't be able to get more vectors here unless you go to larger and larger cells. But you can assume that the matrix is cut off there. So for any capital N you add is equal to 0, and then use the direct sum to determine at other k points. Actually, I never use it myself, as I don't know how well this is good, how well it converges, but there is a way, so to say. All right, so I stop sharing, and I'm happy to answer your questions. Why didn't you stop? Oh, wrong.